everyone. Welcome to our session to Infinity and Beyond. My name's Derek.
My name is César.
And we're both software engineers at ThousandEyes. And what we want to do for today is talk about our scaling journey and some of the transitions that our kind of back-end architecture has gone through in the last couple of years. So this might sound a bit weird, but our scaling challenges actually began because of COVID, and we'll go into a little bit more detail later explaining why exactly this is the case. But because of COVID, our product or our backend had to handle traffic at a much larger order of magnitude, and we had to scale quickly while maintaining stability and not introducing any downtime. So what we'd like to do for today is not to go into anything too technical, and we won't be showing you any code. But what we'd like to do instead is tell you a series of stories of how we scaled our architecture, some techniques and patterns that we've adopted, and some lessons that we've learned along the way. And hopefully we're able to leave you with some practical tips, tools, and insight that you can adapt to scale your systems as your products grow.
Okay, so before we dive into this scaling journey, we would like to give you a bit of context of what we're working on, and so you can understand the challenges that we're trying to solve. So ThousandEyes has multiple products, but today we will focus on one called the Endpoint Agent. That's the product that Derek and I are working on. So what are we trying to solve? Well, imagine in the morning you're trying to work, and as part of your daily activity, you need to connect to GitHub, and suddenly for some reason you cannot connect to it. So you might call your IT admin and say, hey, I cannot connect to GitHub. And you're kind of putting them in an awkward position because it could be so many things going wrong. It could be GitHub having an outage. It could be something happening on the internet. We think of the internet as this magic box, but it is actually a bunch of servers that can fail as well. Or it could be something locally. You could have a problem in your VPN or in your Wi-Fi or in your gateway, things like that. So how do we solve that? Well, thanks to the Endpoint Agent. So this is so here in Agent, we basically mean it's like a C++ program that we can install on your laptop. It's like an app. So we can install that. And the first thing it can do is it can do what's called a network test. And think of it a bit as a ping. And it's going to ping GitHub at a regular interval that you can define. And this will basically make sure that you can reach at a given site, like here GitHub, and we can do different type of measurements. What we can also do is we can look at local metrics, things like your Wi-Fi, your gateway. We can look at your browser experience. We can look at VPNs and proxy that you might be connecting to. And we can also look at performance, like how much memory you have available or how much CPU. And so with all of this information, IT people are actually able to pinpoint and say, OK, this is the reason why you're not able to connect to GitHub. So I kind of mentioned, again, this concept of network test, and that's not something that I was familiar when I joined ThousandEyes. So what is it? Well, again, think of it as a glorified ping. So here we can see on the UI, so this is from our user interface. So this is something that an admin would set up, not you. And you can here the most important is the URL, and then you can say the interval. So here we're going to say, I want to test to GitHub every 5 minutes. So then once you save that into our backend, into our UI, this will be downloaded into the Endpoint Agent. And then the Endpoint Agent will start pinging GitHub at regular interval, here 5 minutes. And every 5 minutes is going to send metrics back to our backend. So what sort of metrics? Well, for network, we have standard things like loss and latency and jitter. If you're targeting an HTTP endpoint, we can look at availability, response time, and throughput. And really, the crown jewel of the ThousandEyes is something called the path trace visualization. And this is kind of why when our families ask us, oh, what is it that you're working on? We tell them, well, we are the Google Maps of the internet. So I don't know if you've played with a terminal and a command called traceroute when you're trying to target an address and it's showing you all the hops that you're going through. This is kind of this on steroid and kind of pretty as well. So you can see on the left we have the different endpoint agents, and on the right we can see the 3 IP addresses that corresponds to GitHub. So clearly you can say that GitHub has multiple servers depending on the regions, and we can see the Wi-Fi they're connecting to, the VPN, the proxy, and if there is any loss, the network engineers are able to pinpoint where that loss is, and this is actually a very powerful tool for network engineers. Just to give you a little bit of context, these are some of the customers that are using ThousandEyes in general, not just Endpoint Agent. So we have quite a wide range of industries and sizes. I think what's quite interesting is that we do have a few tech-heavy companies. And these companies, when they have a technical problem like networking, they tend to solve it themselves. but networking is hard, so they've been actually trusting us with that for several years now.
So before we talk about any of our kind of scaling journey, we want to give you an overview of our architecture kind of pre-COVID, just to set the scene and context for some of our later topics. And when we look at our backend, it primarily has two major clients: the Endpoint Agent, which is the thing that's in charge of collecting these network measurements, and the UI, which is in charge of visualizing and displaying this data. When we think about a backend, we think of it as two distinct sets of services. We have the data plane services, which is in charge of ingesting measurements from the agent, processing them. And we have the control plane services, which is in charge of things like agent metadata. And this is where we tell the agent what network test it needs to run, which endpoint it needs to ping. And then we also have the UI, which queries data from the data plane. And the UI also interacts with the control plane when a user configures a network test for the agents. And since majority of our load actually comes from the endpoint agent itself, simply because we deploy way more agents than we have human users that use a UI. And typically we see 10x more traffic from the agent compared to the UI. And so when we were scaling our backend, we focused more on the agent traffic as opposed to traffic coming from the UI. And so if we dive into the data plane a little bit more and see how the agent interacts with that, we have an ingestion service, which is initially in charge of receiving the measurement from the agent. And as part of the ingestion, we will call out to a MongoDB cluster for authentication and a MySQL cluster for validation. And this will be for things like, is this agent enabled or disabled? Is it allowed to submit this, this measurement, this data point? When everything is OK for ingestion, we will push that into a Kafka queue, at which point we'll return 200 OK to the agent, and the agent will be able to submit its next batch of data points. And if anything goes wrong in this process or there's an error, we'll return an error code to the agent, and the agent will retry the batch of data points that it just tried to submit. And this idea of retries is something that we'll revisit later in this session as well. After ingestion, we have a enrichment service, which subscribes to this same Kafka queue, pulls the data point out, and performs various enrichments on top of the data point. And so, for example, one type of enrichment we perform is we will try to figure out the location of the agent that submitted the data point and enrich the data point with the location. And this allows us to provide more context for our users when they're actually viewing the visualizations on the UI. And similarly, as part of this enrichment process, we will also call out to the same MySQL cluster that the ingestion service uses. We also call out to a Redis cluster and some external microservices. Once enrichment is complete, we will push this enriched data point back into Kafka, at which point it's picked up by a storage service, and we will basically push those data points into a separate MongoDB cluster and Elasticsearch cluster. And these MongoDB and Elasticsearch clusters is what's used by our UI to actually visualize and query the data points. The data points themselves are also pushed to some external services to power features like alerting. So for example, our users can set up alerts to say, hey, notify me when a given measurement exceeds a threshold. So we also push it to external services. Moving on to our control plane, we have a service called the controller, which is primarily in charge of handling two types of requests: a heartbeat, where the agent tells us that they're still online, and this happens every 10 minutes, and a configuration polling request, which also happens every 10 minutes. And this is where our controller tells the agent, this is the configuration you need, these are the tests that you need to run. And so as part of handling these two requests, our controller will also call out to the same MongoDB cluster for authentication, and it calls out to the same MySQL cluster for the configuration that the agent actually needs. And in order to generate this configuration, we have a service called the scheduler, which saves the configuration into MySQL, and it reacts off of events in Kafka. So whenever a configuration is changed by a user in the UI, this is published as a message to Kafka, which the scheduler then reacts on. And so as you can see, our architecture was far from perfect. Services were sharing databases with each other. A lot of requests were actually quite inefficient. But at that time, we didn't really have much traffic, and we didn't really have to optimize or scale for anything. And in fact, in those days, we would jokingly refer to the Endpoint Agent as a glorified science project. And marketing probably isn't so happy with me telling you that, but that was the case at the time. Our traffic numbers were really pretty low. But when COVID happened and all our companies started moving to remote work, suddenly it became really hard for your IT admins to troubleshoot your networking setups because we're all working from home, we all have different networking setups. And so going back to the previous example, if you can't access GitHub, that's pretty detrimental for your productivity, right? And you'll call your IT admin and say, hey, I can't access GitHub. But it's really hard for your IT admin to figure out, is it a problem with your local device? Is it a problem with your Wi-Fi router at home? Is it your local ISP, or is there a wider GitHub outage? It's really hard for them to answer these questions. But with the endpoint agents, we will collect data and really help the IT admin and network engineers start answering some of these questions. And so someone from ThousandEyes had the bright idea to offer the endpoint agent for a limited time free trial because of COVID, and the goal was to help companies kind of debug some of these networking issues because now all of a sudden we all have this huge dependency on the internet and we don't have any visibility into it. And so here's a graph showing the number of endpoint agents. And that uptick there is when we first announced the free trial, and this was really when we let the floodgates open and our scaling journey kind of began. And so we had a few ideas of where bottlenecks in our systems might be. But we really wanted to validate, like, where was it the most valuable for us to spend our time? And since we were expecting an influx of traffic, we decided to build out a suite of load tests in order to discover where some of these bottlenecks in our system might be. Here's a relatively loose definition of load testing. But what we were really trying to achieve is figure out how our backend would behave if we had to support 30,000 agents, 60,000 agents, or even 100,000 agents. Would our data plane be able to keep up with all the measurements that the agents are sending us? Will there be any issues in our control plane because the agents are polling every 10 minutes? Which components or databases will fall over first? These were some of the questions that we wanted to answer. And so we built out a set of load testing simulations using a tool called Gatling, and Gatling is also a sponsor for today. But what Gatling effectively allows us to do is simulate the behavior of the agent by writing some code that says, hit these HTTP endpoints every X minutes or seconds. And then Gatling will take this code, run it on multiple EC2 instances and VMs, effectively simulating multiple agents hitting our backend at the same time. And when we started with the free trial, we started writing simulations for 30,000 agents, but these days we're running simulations for 300,000 agents. And the goal is to identify bottlenecks in our systems before they become issues in production. And so if you're also considering load testing your systems, one thing that's really useful for us was having good operational visibility. Fortunately, we had great observability tooling, and so it was really easy to monitor our systems and pinpoint where problems were. But I'd go as far as to say if you want to start on a load testing exercise, having good observability tooling is almost a prerequisite. So I dug out some dashboards of our initial load tests, and this is a dashboard showing HTTP response time. And as the number of agents ramped up in our load tests, our response time peaks at 7 minutes, which is pretty bad for an HTTP endpoint to return. Like 7 minutes is pretty bad, but it gave us a good place to start, right? We also considered things like pipeline end-to-end latency, which is a metric that we keep track of, and it measures the time from when an agent uploads a data point to our backend for it to travel through our entire data plane and finally land in our data store. And as you can see here, as we're ramping up the number of agents in our load test, the end-to-end latency peaks at 23 minutes. And given that our SLO is 1 minute for end-to-end latency, again, this is not very good, but it gave us an idea of where some of the problems might be. Finally, we also considered things like application performance monitoring, which allows us to see in a single microservice how much time it's spent on database calls, on external microservice calls, in a single request. And this was really useful for us to drill down from those high-level metrics I showed earlier to application-specific behavior. And all this data was really useful for us when it came to optimizing our systems because we could make a change, rerun the load tests, and compare the metrics with the previous run to verify that our changes actually had an effect. And so even today, we're still running load tests to make sure we're not accidentally introducing performance regressions into our system.
Okay, so now that you have some, sorry, one second. Now that you have some context about what we're trying to solve and what happened during COVID, we will start sharing a few stories with you that how we went on that scaling journey. So we kind of said that we had load testing to find the problems before they became issues in production, and one of the first bottleneck that we found was around this test configuration that we mentioned. So just a reminder, this is what we call the control plane, and remember that the endpoint agent is polling every 10 minutes, asking the controller, hey, give me the latest set of configuration, and that request hits MySQL. So during load testing, we realized that basically we were completely overwhelming MySQL. And unfortunately, for some legacy reason, MySQL was one of the first databases introduced at ThousandEyes, and it's used by other products, which means that we need to protect it. We cannot allow a big surge of endpoint agent traffic to take down other ThousandEyes products. That is not acceptable. The problem as well is that we're not getting consistent performance from it because there are other teams and products that are competing for the same resource. And finally, it's a bit hard to load test because when you do a load test, what do? Do you start an empty MySQL cluster and you just simulate your own traffic, or do you also try to simulate other products' traffic? So that's kind of not really working. So we could say, okay, how about we change the interval of how often we're polling for configuration? Well, the problem is that if you poll too infrequently, then it's going to take a long time to propagate the change. So if a user goes into the UI and changes, for instance, the URL for a test, if it takes 10, 15, 20 minutes to appear, it's really not a great user experience. And then conversely, if we increase the polling interval while we're putting even more load on MySQL, then actually test configuration changes is quite a rare event. It only happens a few times. So this is really like unnecessary load. So the solution for us was, well, how about if we could push the change of configuration to the agent instead of having the polling? So coming back to the control plane, we already had this set of services which we call the scheduler, and that was already built as a reactive system. So we already had Kafka event generated for a specific agent when the configuration changes. So what we did is that we created a new service, which we call the WebSocket controller. That service would subscribe to the Kafka queue that corresponds to the configuration, and then the endpoint agent would open a WebSocket connection, and every time there's a new change, we can push that change, which means that now we don't need to poll, and we've significantly reduced the load on MySQL for that particular use case.
And the kind of next thing we also learned from the load test, in the same theme as protecting this shared legacy MySQL cluster, was that we wanted to cache some of this data in MySQL. And while some of the data in MySQL could be pushed to the agents, we were still using it in the ingestion and enrichment phase of our data pipeline. And since we wanted to protect it and we didn't want to bring it down, causing outages for other products in ThousandEyes, we decided to go to the tried and true formula of caching some of this data. And since we were already using Redis in our data pipeline, and one of the primary use cases for Redis is caching, we decided to leverage it further for this use case. And so at a high level, we followed two patterns for caching. The more familiar and probably simpler one is the read-through cache. And this is where the service will first query the cache, which is Redis in this case, for the data that it needs. If it's there, then we're good to go. It'll just return the data. If it's not there, then it'll go to the source of truth, which is MySQL in this case, for the record. And on the way back, it will populate the cache with the record. When we're populating the cache, we also add a TTL, or an expiry time, on the record, so that Redis will eventually delete the expired entry. And this is so that if the record changes in MySQL, Redis doesn't store the stale value for too long. And so obviously here there's a trade-off between like stale data and cache hits. And fortunately for us, we were able to tolerate some level of data staleness, but that kind of depends on use case to use case, and it's configurable by the TTL. The second caching pattern is the right behind cache. And so for some of the data in MySQL, we were actually asynchronously generating an event in Kafka when a given record was changed. And this was used to power some of our existing asynchronous and event-driven workflows. And so what we found we could do instead was also to subscribe to this event in Kafka to populate the cache in Redis. And effectively, this allows us to keep Redis, the Redis cache, in sync with the records in MySQL, because whenever an event is published, we would update the cache. And so then our service became really simple. It could just query Redis directly without having to go to MySQL. But similar to the read-through cache here, we have a chance of the data data in Redis being stale, because if we haven't yet processed a given event, then the data in Redis won't be the most up-to-date. But again, in practice, we find that Redis is typically 50 to 100 milliseconds behind MySQL, and this was a level of lag that we were able to tolerate. And so we go back to what our data plane now looks like. In the case of the write-through cache, we've completely removed the dependency on MySQL, and we're querying Redis directly. And in the case of the read-through cache, sorry, write-behind cache, in the case of the read-through cache, we've severely reduced the amount of traffic to MySQL and front-loaded a lot of that with Redis instead. And when we reran the load tests, we were able to see much better performance, and MySQL was no longer being a bottleneck. And so the main learnings for us from caching was that caching is really an exercise in trade-offs. You're trading off data freshness for better performance. And with a lack of data freshness, that usually implies eventual consistency. And I think for us, we were initially hesitant at operating on stale data. But when we really sat down and thought about our use cases, most of the time we don't need data freshness, and eventual consistency is actually OK. And this is something that we've kind of embraced more and more throughout our development process. And eventual consistency is also a thing that we'll talk about later on today as well.
OK, so now we said that we're doing load testing to find problems, bottleneck before they become problem in production. Well, sometimes you miss things, and we had to learn some lessons the hard way. So this is one of them around retry policies. So to understand this, maybe we can drill down a little bit more into the endpoint agent. So we already said that endpoint agent receives the configuration from the control plane. This goes into a process we can call the test runner. So the test runner gets the config and then starts pinging a given website or service a website, and then stores the data internally in a queue. And then we've got a separate process called the data uploader that is responsible for pushing that data back into our data plane. And so like we mentioned already, we have retries. So here in this case, we have timeout, so 3 seconds. And we had exponential backoffs in place with a maximum backoff of 1 hour. And so if the data plane is too slow, or if it returns an error code, the data point is not lost. It just be retried until it gets a 200 from the backend, from the data plane, and then it's OK, we can remove it from the queue. OK, so this is kind of like, this is how it should be, and it looks good. OK, so what happened on that very nice day that we had? It all started with a Kafka maintenance. So like everyone, we need to maintain our infrastructure. And most of the time, we can do that without any downtime. But sometimes there's certain type of maintenance that require a little bit of downtime. So this was one of them. And I think for between 5 to 10 minutes, our data plane was returning 400 to the agent, which is OK. That's why we have retries. So the agent started retrying. Now, in a normal day, it's just a handful of agents are retrying for, let's say, random errors that happens. But here, once the maintenance was done, all the agents were retrying all at once. And something that we haven't really said explicitly yet, but your endpoint agent comes online when you come online, when you start working. So we have a bit of a cyclical pattern. And this was beginning of the afternoon in the UK, mid-afternoon. So when Europe is awake and the US is also awake. So we're basically at the peak amount of traffic. So we had a lot of agents online. And so even when the backend was now functioning after the maintenance, because there was so many retries, the response time started to increase. So the data points were ingested into Kafka, but because the data plane wasn't able to say, yes, I got that data point fast enough, the agent would time out and then retry the same data point. Okay? So that was the first cycle of doom. Now, something else happened. Remember that I said that we had a backoff period of a maximum 1 hour. And so what happened is that, so we had this, so this became like an incident. There was like a big call, all the engineers trying to find solution. And after maybe like half an hour, we scaled a bunch of services. OK, yes, we're out of the woods. All good. And then after 1 hour, after the initial big surge of traffic, we started getting a second big surge of traffic. And so what happened is that the agents, they were synchronizing every hour. So the requests were coming, and they were coming in waves. And so that meant that every hour we would get a huge waves of requests, and that would create another increase of response time, and again, they would feedback the whole cycle. And if you're interested, this is something called the thundering herd problem. It's not just it's a real thing, it happens. And so what was the consequence for our customers? Well, I kind of already said that because the agents were retrying data points that they thought hadn't been ingested, but actually were ingested, we had a lot of duplicated data points in our pipeline. We had about 10 times the amount of data that we normally process. So, we have a little bit of bandwidth in our processing pipeline, a bit of elasticity, but not 10 times. So what that meant is that our pipeline was overwhelmed, and we were not able to show the latest data to our customers. So remember, Derek showed this end-to-end latency, which is the time it takes from one data point to travel through the whole thing. Normally, we're well under 1 second. That's the SLO, and here we were like hours. We were completely overwhelmed. And so here in this case, if you think about it, we're deploying all these agents everywhere, and they're all overwhelming us. They're all DDoSing ourselves. So we kind of coined this new term called SDDD, and it means self-DDoS-driven development. So we're very proud of this, and we hope to be the leader of this new way of working. No, so how did we do it? Well, the problem, it might be obvious now, is that there was no randomness into the retry policy. So the agents were backing off, but they were all using the same time. So we had this synchronization happening. So the first solution was to implement something called jitter, which means adding randomness into the retry. And so we looked at, what has happened? We did a lot of testing and trying, we need to figure this out. So we need a bunch of testing, and we felt that the one that was the best for us is one called the equal jitter. So this works in conjunction with your back-off policy. So your policy is, you have to sleep for T, so let's say 60 seconds, and you say, we're going to sleep for half that time, at least 30 seconds, and then the second half is randomized. So it means that the agents are not retrying at the same time. What we also did during these outages is that we would deploy a kind of low rate limit threshold to make sure that our backend is not overwhelmed, and then we would kind of slowly increase that rate to make sure that we can cope. And again, it's going to sound very obvious, but now we make sure that we always have like a default level of rate limiting on all APIs to make sure that we don't DDoS ourselves. So just to show you some graphs. So this is not production. This is like one of the simulations that we did afterwards. So we triggered some fake incident in our testing environment, and we measured the request rate. And you can see here, without the jitter, we had this kind of snowball effect that, big spikes of requests. And after we implemented the jitter, there was just one initial peak of traffic, and then it kind of dies down without this snowball effect. So since we implemented jitter on the agent level, because actually most of the scaling we did that on the backend, but that we had to fix that on the agent, we haven't had any problem, and we have more agent now than we had at the time.
Another kind of lesson we learned in production that we didn't pick up in our load tests is that authentication is really important. And this probably sounds really obvious, and it is, but it can be overstated, because if you're building a product that involves identity, authentication is almost always going to be on the critical path. And so for us, our agents had identity. Whenever an agent submits a data point, we need to authenticate them and verify that they are who they say they are. And when we thought about it, what we're looking for from an authentication system is stability and consistent performance. We need the authentication system to be available all the time, so it needs to be stable, and it needs to return the authentication result in a reasonable amount of time. We don't want peaks of latency. We want flat, consistent latency numbers where authentication is concerned. And so when we looked at our current authentication system using MongoDB, unfortunately, we were getting neither consistency nor stability. We had a few kind of late nights and early mornings where MongoDB just either became really slow or just stopped working completely, and our backend would grind to a halt because the agents just couldn't submit any data points. And when we dug into things a little bit more, we found that the queries we were issuing to MongoDB were actually really simple. They were just find by ID style of queries, which is kind of what you expect from an authentication query. But like the MySQL cluster, this MongoDB cluster was unfortunately also shared with other engineering teams. And so it was possible that a service deployed by another engineering team in ThousandEyes was issuing an intensive query to Mongo, and that would cause our authentication requests to fail. And so obviously that wasn't great, and we wanted to fix it. The other thing that wasn't working for us was that MongoDB wasn't scaling in a cost-effective way, at least not in a cost-effective way that we were comfortable with. So we wanted to look for some alternatives. And considering multiple options, we finally decided on Dynamo as our system of auth records instead. And what we liked about Dynamo was that it gave us flexible scaling options and also auto-scaling at relatively low engineering efforts. And so, yeah, if you haven't heard of Dynamo before, it's a persistent key-value store that's offered by AWS, and it has really similar characteristics as Cassandra. And so the challenge for us was, how do we migrate the authentication records from Mongo to Dynamo without any downtime? We couldn't just turn off Mongo, copy the data over, and turn on Dynamo because that would be too much downtime for us. We couldn't tolerate that. And so one of the engineers on our team had the bright idea of using a technique called change data capture, which is powered by an open source technology called Debezium. And concretely, what we're doing is listening to changes in the records in MongoDB. So whenever a record is inserted, updated, or deleted, Debezium would be notified of those changes and push an event to Kafka. We're capturing changes to that data. On the other side, we have a process that subscribes to these change events, and they would translate them into records that Dynamo will understand, and then push these records into Dynamo. And so at this point, we've got DynamoDB in sync with MongoDB, and we're asynchronously replicating any changes over. And so all that was left to do was turn off the request to Mongo and turn on the request to Dynamo, and we were good to go. And so we just recapped the kind of ingestion phase of our data plane. We've now replaced Mongo with DynamoDB as our system of auth records. And after some load testing, we were able to see much better results with DynamoDB instead. And without a suite of load tests as well, it would have been really difficult to kind of justify this decision and validate it and also sell it to management. And what DynamoDB gave us was much better stability and much more consistent performance, which is exactly what we wanted out of an authentication system.
Okay, so far we've kind of been showing you some of the more like low-hanging fruits that we did as part of the scaling journey, but we also had to do large re-architecting, and this is one of them that we wanted to share with you, and it basically boiled down to separating the reads and the writes. So let's give you some context. So this is called the agent settings page. So this is as part of our UI, and you can log in and you can see all the endpoint agents that are installed within your organization. And you can see which versions they're running, where they're located, when was the last time they had a heartbeat. You can search by name, because there could be quite a lot of agents in one organization. It's like one agent for all employees. If you have a very large organization, that can be a lot. You can also filter by a lot of different attributes. And if you click on one endpoint agent, you can see some details about the agent, what test it's running, and you can do things like change the agent name. And so we had a request from the product, and they said, because historically we had a limit of how many endpoint agents we can have per organization, and the product said, hey, what if we use 5 times the number of agents? I said, okay, all right, well, we can load test that. So we created a fake account. We added 5 times the number of agents that we normally have, and that page became extremely slow. So it would take around 10 seconds to make any request on that page, which is not acceptable. So why was it so bad? Okay, so basically this page is pulling what we could call the agent metadata, and for legacy reasons that we can't really explain here, this data was spread into multiple data stores. So the first type of data, which we could call the user actions, are things like, I'm changing the name of the agent. Okay, and that was in one MongoDB cluster. Now, the agent, remember that it's doing a heartbeat, and this heartbeat contains a lot of information, things the location, which Wi-Fi is connected to, some MAC address, IP settings. So all of this, again, for legacy reasons, were into a separate MongoDB cluster. It's really not great. And then, again, for even more legacy reasons, we still had some license management information in MySQL, things like is the agent enabled, disabled, like license count, things like that. And so to be able to serve agent metadata as a whole to this agent settings page, well, we had one service that had to pull the data from all this data store, combine it in memory, and then serve it. But you've seen on the screenshot that we have filters. And these filters, they apply on multiple data stores. So you cannot filter at the database level. The only thing you can do is pull the entirety of the data set from all data stores, combine in memory, apply filtering, apply pagination, and then return. And that is, that's why it was very slow. So we had to do something about that. So what did we do? Well, we had a bit of a brainstorm, and we were thinking, okay, we can't really change the different types of writes. This is something that, it is what it is. And we kind of said, okay, For us, Elasticsearch has worked really well when we're dealing with a lot of filters, because Elasticsearch can index on a lot of different fields. So if you need to have a large data set that you need to filter, it's great. So we said, okay, we would like to have agent metadata in Elasticsearch. Okay. However, we've just talked about that. For authentication, we also need agent metadata, but for this, we need to be able to get it by ID in a very fast and consistent manner. Well, actually, in this case, DynamoDB is the best tool for the job. And who knows, maybe tomorrow we've got another use case and we need a different database. So we thought, okay, well, we want to have it all. We would like to use all these data stores, and they could be some sort of glorified cache, but we still need to have a source of truth. So what is the database that would give us, that should be the source of truth? And actually, we decided it should be Kafka. And up until that day, we were only using Kafka as a transient data store to, we have our data points, they go into a Kafka queue, and then because they eventually get stored into Elasticsearch or MongoDB, after several days or a week, we expire them because there's no point keeping that. But we can actually use Kafka as a real database. And why is that? Why did we think it was a good idea? Well, if you have agent metadata in Kafka, and every time there is a new change, you send a new message, well, it's very easy to subscribe and to have one subscriber for each data store. And with this pattern, you can have as many data stores as you want, and it will keep all of these data stores in sync. So how did we go about that? Because this was quite a large refactoring. So this is kind of how it was before, when we started. We had those 3 types of write actions, and they would each just make a direct write to one of their database. So the first thing we did is that we stopped writing to the database, and we made those write actions call a new service, which we call the agent management service. And what would this service do when it receives the write request? It would write an event into a Kafka queue. And here this event would be like a change event, like a diff. So for instance, if you change the name of the agent, in this message you would just say new name and the name. It's a very small message. It doesn't contain everything, just what has changed. And then, once we had that, it was relatively easy to consume that for each data store and apply the corresponding change, so that it would basically be exactly the same. So we have exactly the same access pattern. The only difference now is that we are eventually consistent. That before, when you would make a write in the UI, it would go straight in the database. Now it needs to go to Kafka and then be consumed and be applied. So there is eventual consistency. So that was the first step. Then, what did we do? Well, these Kafka events, we could use them in a different way. And we had another service called the agent updater that would subscribe to those diff events. And the role of this agent would be to maintain the source of truth in Kafka. So how does it work? Well, it will subscribe to the latest version of that agent. Then it would, once it gets a change event, it would apply that diff, and then it would save it back into Kafka. Now, it's not to talk about Kafka. We don't really have time to go into details, but the reason why this works is that with Kafka, you can partition data with a given key, and here we use the agent ID, and Kafka guarantees that the message with the same partition key are processed sequentially. So if you have multiple writes on the same agent, they're not going to happen at the same time. They're going to be processed one at a time, and this means that this works. And then once we had that, it was easy to then consume from Elasticsearch. And then once we got here, okay, now we did something called shadow testing. So we made the request to the settings page like we normally would, and then we made a similar request to Elasticsearch. We compared the data, and we make sure that we have the same thing, and we fix a few bugs. And once we were happy with that, we switched the traffic to serve the page from Elasticsearch, and we don't have to query all this database. And in terms of performance, what does it mean? Well, we went from 10 seconds to 100 milliseconds. And that means that the page was not only it was much snappier to use, but it means, okay, now we can actually scale to the extra load that was needed by the product. So what did we learn with this big exercise that it took almost 2 quarters to deliver this? We spent a lot of time designing this upfront. So, I mean, here we've simplified a little bit, but we didn't come up with this on day one. We had several iterative, even the idea of having Kafka that came after. At the beginning, we said, oh, we'll put it in Elasticsearch. And later, well, actually, it would be better with Kafka. So we had to invest upfront this time. And we think it was worth it because after that, the code change was relatively straightforward. We had a fixed plan of how to do the code change and then how to slowly release, like I've shown. So we were happy with that. Now, unfortunately, the rollout in prod wasn't without its problems. We had some corner cases in the production data that wasn't the same in the test data. So we missed a few things. But we got there in the end. It was a bit longer than we thought. One thing that we wanted to do as well is that we knew that the endpoint scaling journey was just beginning. So we wanted a solution that is future-proof, because if you think about it, the requirement was scale just that one page. And we did a complete re-engineering. So it kind of like, oh, you've engineered that. But we knew that this was a really bad legacy system that we had, and we had to do better. And actually, this is already paying dividends, because recently we started an integration work with another team at ThousandEyes. And what they needed to know every time agent metadata changes. So if it wasn't for that, they would have to start polling multiple data stores, which would be horrible. But now, oh, we already have a Kafka queue. They can just subscribe to it. We don't even need to know about it, and they can know when we have changes. And finally, again, it's something that we mentioned several times, just be careful with eventual consistency. So for us, we've been very happy with it, but you have to be aware of it. So before, if you go to the settings page, you make a change, it goes straight into the database. Now, it goes into Kafka, and there is a bit of a lag. And for us, it's around 100 milliseconds, and we are happy with that, and we have alerts on that lag, and we have Grafana dashboards. But it's an additional complexity that, you have to know what you are signing up for.
Right, and the last kind of, I guess, lesson that we want to talk about is probably the least technical topic for today. And it's that when all else fails and you simply can't scale anything further, sometimes it's okay to introduce some limitations and trade-offs into your product. And in our experience, and I guess contrary to popular belief, product managers are actually pretty reasonable people. And most of them would prefer a limited functionality over just a completely broken product experience. And so one example for us was the path visualization views. And so if the graph in the path visualization was simply too large to render, we would just return an error message and ask the user to add some more filters to constrain the data set. Another example of a limitation we had to introduce was throttling the rate at which new agents could be registered with our backend, because the registration code path was just not optimized enough. But really the takeaway here for us is that while scaling is predominantly an engineering challenge, not every scaling issue needs to be solved with engineering completely. And sometimes it's okay to introduce some limitations into your product to protect operational stability. And as we all know, at the end of the day, it sounds cliched, but in engineering, everything is a trade-off. And so we'd like to close off with some of the key lessons, or what we felt was some of the key lessons in our scaling journey so far. Without load testing, many of these problems that we've presented would have probably be discovered in production, most likely during an outage, and it would have been very difficult to fix it then and there. Additionally, load test also allows us to make sure we're fixing the right bits of our system, and we're not just spending time optimizing something that doesn't need to be optimized. And so even today, we're still running load tests to make sure we're not introducing performance regressions, and we can scale our system further. The other thing that we've come to terms with about our system is eventual consistency. And with eventual consistency, we were able to get much higher levels of load and much better traffic. And we found that most of the time we don't need consistent data. Having data consistency is quite expensive to maintain, because typically it means you need to shove everything into a same database and read and write from the same database as well, and you need to vertically scale that thing, and that's difficult. But with eventual consistency, we were able to unlock much higher levels of load. But obviously, this is something, your mileage with eventual consistency might vary, and whether you adopt it or not depends on your product and also your use case. And finally, it pays to revisit your distributed systems fundamentals. Things like exponential backoff and jitter, caching, sharding, and data partitioning. All this stuff works great, and it's been well researched. It's not just for the technical interview. It actually works on the job as well. And so, is this the end for us? We hope not, because this is a graph showing the number of endpoint agents over the last 2 years. And we're cautiously optimistic that this trend will continue. But what we hope we had done today was show you our scaling journey and some of the performances, some of the regressions or bottlenecks that we found, but also how we fixed it. And hopefully we've helped you avoid some of the pitfalls that we've encountered and inspired you on your scaling journey. Thanks.
Yeah, we have time. So we've got time for some questions. We're all trying to look at them online. Do we have any?
Yeah, there are 4 questions.
Okay.
So the first one is like, where are you testing? Where are you doing the load testing? In which environment?
So the question is, in which environment we're doing? Oh, okay, that's good. Yeah.
Yeah. So the question is like, where are you running your load tests
Do you want to go?
against? In which environment?
Yeah, so we actually have a dedicated load testing environment where we spin up databases that are scaled to the same capacity as production, and we run load tests against that load testing environment. So yeah, we don't run load tests against production, we run it against a dedicated load testing environment.
Okay, and in terms of load test scenarios, how do you come up with the different scenarios?
Yeah, so to come up with the scenarios, we basically looked at the behavior of the agent itself, and we worked together with the team that works on the agent, and we effectively simulate that behavior. On average, the agent would submit data points every 5 minutes to our backend, and so we would write that into our simulation.
Okay. You also mentioned the different observability tools that you used. How do you use them to troubleshoot issues and verify your changes? What kind of metrics do you focus on, etc.?
Okay.
Yeah, so there's loads of metrics. The few that we showed, kind of high-level ones, like HTTP response time, we obviously want that kind of relatively low. The pipeline end-to-end latency, we want that within our SLO, and also, I guess, HTTP availability as well. So, we want 4 nines of availability, and also, stuff like application performance monitoring, which we showed earlier. We use that more as a, I guess, diagnostic tool. But there are also some other kind of database-level metrics that we will look at in order to help us diagnose some issues. Like we would look at, heap size in Elasticsearch, data,
CPU,
yeah, CPU, disk size on Kafka. Yeah, a whole bunch of things. But yeah, I think we tend to drill down from the higher level metrics like HTTP response time, kind of high level latencies, and then we start looking at data store or APM.
Yeah, I don't know if I want to share this one, but recently we had a typo in the configuration in Elasticsearch, and instead of having 5 shards and 1 replica, we had one shard and 5 replicas. So suddenly, when we started to the next day, all the data was going into a single node, and we see like a big spike in CPU, and Elasticsearch was like, no, I cannot cope anymore. And then, yeah, it took us a bit of a while to say, oh, okay, that's a typo, and let's revert that quickly.
And the last question in the app. So how do you avoid blockages in the pipeline, such as during the enrichment phase while being read from Kafka?
How do we avoid blockages?
Yeah. Yeah, so I guess, if there's a bug in our code, let's say, and we process data point and it's throwing an exception and keeps trying again and again, then we would fix the bug. And then if there's actually a data point that is invalid that made its way into the pipeline somehow, then with Kafka, you can actually advance the offset to the next one, effectively skipping that kind of invalid data point. And then we also have things like dead letter queues, where if for whatever reason we're erroring out on the same data point over and over again, we would put that data point into a separate Kafka queue, which we call like a dead letter queue or a discard queue, and then we would kind of inspect that later to see what exactly went wrong, so it doesn't block the other data points from being processed.
We also started something that we do if we have an incident and we have a lot of lag. So we're building up a lot of data points. So for instance, it's 12 and we're still processing data point from an hour ago. So what we kind of do now is that we reset the Kafka lag to right now, which means that the most recent data is flowing through the pipeline. And then we spin up in parallel a separate consumer that then works on the lag. So that kind of means that as a user, you will be missing data from the past, which is maybe not that important, but you're still getting data right now. And then, several hours later or whatever, we start filling up the data. And this is something that we've been trying to do more and more now.
Do you have any reason to choose Elasticsearch over other indexing systems? For example, Solar.
Yes.
Was there any reason for that?
Yeah, so the question was why we chose Elasticsearch over other similar DBs. And I think we were already using Elasticsearch in our product, and we had expertise, and we were familiar with how it worked and how to query it effectively. And so that's why we kind of went with it. There wasn't, when we joined, Elasticsearch was already used quite widely in the system, and so it was something that we just went with.
Yeah, I think also we had very positive emotional experience with Elasticsearch. It just works, and if it doesn't work, you just add a few more nodes and then it works, and it's been like, I don't want to say other databases, but no names, but one of the good ones in terms of developer peace of mind.
So all the infrastructure, backend infrastructure infrastructure, is it on Amazon?
Yeah, so the question was like, is our infrastructure in Amazon? And yes, it is. Yeah, we run on AWS. Because yeah, we use Dynamo, as I showed earlier, which is an AWS service. A lot of our stuff is also on AWS. Yeah.
But because we use Kubernetes, it's almost, we don't really know. Like for a while, we were running on-premise, and then we moved to the cloud, so we had a mix. Because with Kubernetes, that's the whole thing with Kubernetes, that you abstract away your hardware. So it doesn't really almost it doesn't really matter. You just need, you need nodes with the Docker that can run your containers. But yeah, we're trying more and more to use more and more Elasticsearch services. Even Redis, for instance, we use the
we use Elasticache.
Yeah.
We've got one more from the live stream. Someone asked, did you also consider running a prod parallel setup as a separate consumer group for the load testing?
Yeah, that's a good idea. And it's something we've considered, but it was just, it was a lot of kind of engineering effort to kind of get that working. And we didn't have the maturity or like tooling at the time to get that to work. Yeah, we did consider it, but we needed to build out a load testing environment relatively quickly. So prod parallel wasn't something we considered given how much engineering effort it takes. But it's definitely something that's on our mind, and we're trying to figure out how that would work.
Yeah, I think we had 1 or 2 weeks notice about this COVID promotion. Where we told, hey, by the way, we're gonna do this discount. What? Sorry.
Yeah.
And then we basically had to scramble and
Cool. All right, I think we're.
There was one more question at the back now.
Yeah. Oh yeah, sure. Yeah, go.
Just going back to load testing as well, what's your strategy in terms of when you run your load test? Is it part of your CI/CD, or have you got scheduled jobs? How does that work?
Yeah, good question. So right now, load test running is manual, so we have to kind of do it every week, and someone has to go into the load testing environment and actually press the button. But yeah, we're trying to automate that, put it as part of a pipeline or something like that, so that it kind of runs more regularly and we can get better results. But yeah, we're working on it. At the moment, it's manual just because we haven't had the time to invest the effort into automating it.
Yeah, we're giving you the honest answer. We could have said, oh yes, of course, automated. Not yet.
Yeah, we're working on it.
But we were hoping it would be.
Yeah. Cool. So I think we're more or less out of time. But yeah, if you have any more questions about this, feel free to chat to us. We're around for the rest of the day.
And please give us feedback as well, and rate the talk if you liked it or if you didn't like it as well on the app. Just give us feedback as well. Thank you very much.
Thanks, guys.